Most programs need to be able to work with numerical data that's more precise than just integer values. So how do we represent decimals? How do we represent fractional values and percentages? Well, if you've programmed before, you've probably encountered floating point numbers, and you've realized that they're not named just decimals. So there must be some difference between a decimal and a floating point number. And that difference is in how these numbers are represented and some of their limitations and constraints. Before we get into the details of floating point representation, which will be in the next video, we first need to understand what we know about fractional numbers and translate that understanding into fractional numbers in binary. And then we're going to take that knowledge and think about, well, how can we, given the constraints of fixed size number of bits in our bit fields, how can we actually represent these numbers and still have a lot of flexibility in the numbers we're able to represent? So let's jump into fractional numbers. To begin with, I want you to look at the fractions represented on this slide and think about what are their decimal representations. 1/2, 1/3, 10 1/4. What are those numbers represented in decimal? So pause the video here if you need to, but I think you're probably able to translate these without even really thinking twice about them, right? We know that 1/2 is 0.5 in decimal notation. 1/3, the fraction, is 0.3, and then the 3 is repeating, right? So we've got a non-terminating repeating decimal number. And 10 1/4 here is 10.25. How did we get from 1/2 to 0.5? There wasn't even a 5 in the original encoding of 1/2, right? Well, you kind of know that there's a trick here. And the trick is, well, if we converted that 2 to 10 by multiplying both of the numerator and the denominator of this fraction by 5, we would have 5/10, and that's the same as 5/10 represented in this decimal notation. You also know that there's an algorithm for making this conversion that we learned in elementary school, right? So how do we go from a ratio or a fraction to a decimal? Well, long division, right? So it's been a while, most likely, since you've practiced long division, but this was the algorithm you were taught. And one of the first algorithms you were taught, I should say, for making a conversion of this kind. And there's some interesting rules. This was one of the first reasons why you needed to know how to take remainders, and you calculate a remainder as part of doing long division. So what I'd like you to try doing, and I do want you to actually pause the video at this point and try working out the long division of 1/8 and 9/11 to convert both of these values into decimal representations. And go ahead and work this out. Try and work through the steps of the long division in your own time. Pause the video here, and then we'll come back and review. All right. So let's talk through 1/8, right? So we're saying 1/8. And if we wanted to use the long division algorithm, we'll tend to put the 8 before the 1 under this divisor and work it out. So we're asking ourselves at this point, how many times does 8 go into 1? And we're thinking about this in terms of integer division, right? 0 times, right? So 0 is the number of times 8 divides evenly or into 1. So what do? Well, we say, okay, we've run out of digits here, so we're going to say that whatever comes after this is going to be a decimal number and represent fractions of a number. So when we add this decimal, we can then extend this number out, right? We can add zeros as we need to the number underneath the divisor here. And we're saying, okay, well, now how many times does 8 divide evenly into 10? And 8 divides evenly into 10 one time, right? So we multiply 8 by 1. And here what we're doing is we're calculating the remainder of this operation, right? So we have a remainder of 2 when we divide 10 by 8, right? And so one of the things that I think is kind of interesting about programming is we spend so much time talking about the remainder operator and the modulus operator, which are commonly used in many different cases in computer algorithms. Well, here we're seeing this was used in an algorithm that you learned early in your life for calculating, making this algorithmic conversion between a fraction and a decimal number. So how many times does 8 go into 2? Doesn't. So we again extend by a 0. And now we ask how many times does 8 go into 20? or what is that integer division operation? And so we know that 2 times, right? 8 times 2 is 16. And so we multiply 8 by 2 and we get 16. And now we take the remainder here. And the remainder of dividing 20 by 8 is 4. Right? And so now we say, okay, well, how many times does 8 go into 4? It doesn't, right? It's 0. So we once again borrow another 0 here. And now we're asking how many times does 8 go into 40? 5 times, right? So 5 times over. So we multiply 8 by 5. We have 40 again here. And we take the remainder of that operation, and it's 0. And so the terminating case in the long division algorithm is when you reach a remainder of 0 after you've calculated your decimal places like this, right? So that's a number that has a terminating decimal representation, a fraction that has a terminating decimal representation. I'm not going to walk through this example. I want you to try doing that on your own and convincing yourself that you can, but this is a non-terminating decimal number. So if you just calculate out to 4 significant digits, that should be enough to prove that you are getting the gist of and remembering how the long division comes together, right? So that's long division, and that's the algorithm that we use to convert between a fraction in base 10 and a decimal representation in base 10. So how do we think about this number for each of its placeholders, right? A decimal number with a decimal point or with a positional decimal here. So notice we're representing the decimal point here in the middle. And we're saying we've got 4 digits that are part of the whole number and 4 digits that are part of the fractional number or the fractional makeup of this, right? And how do we think about how these positions are related to one another? Well, when we were looking at integers, we reminded ourselves that this is the ones position, this is the tens position, this is the hundreds position, and this is the thousands position, and so on, right? Where each position represents increasing the magnitude of the digit in that position by an order of 10, and that's how we encode larger and larger numbers using a fixed size number of digits, right? We just string more of them together. Well, similarly, we do the same thing in the opposite direction. But notice that we start with the tenths position here, right? So this is the tenths if we were to try and pronounce this, right? Because we're taking 10 to the negative 1, which is, as we'll see, the fraction 1 over 10. And similarly, as we move in each position, the hundredths position, the thousandths position, and so on. So we think of these as fractional values where what we're doing is we're increasing the exponent, but we're keeping this in the denominator. We're saying this is 1 over 10, 1 over 100, 1 over 1000, and so on. Right? So if we wanted to compute, given a sequence of digits, what is the actual decimal value of some sequence of digits? Well, if we know that we have this many whole digits and this many fractional digits, and let's say we add like 2 here and 3 here and 4 here, what we would do is we would say, okay, multiply 2 times 1, that's going to be 2, and we're going to add that to 3 times 1 over 10, so 3 tenths, added to 4 100ths, and we add these values up, so this would be 30 100ths, and we could get 2 and 34 over 100, or 2.34, oops, I said 4 and I wrote 5, 2.34, which is what we started with, right? And so there's got to be a way of converting these two things. And just as we looked at with binary integer representation and decimal integer representation, we can formalize this by thinking about a decimal digit vector. So here, we're going to have a decimal digit vector d, which is just going to be a sequence of digits, right? But this time around, we need to differentiate or specify what are the whole digits and what are the fractional digits. And the way that we're going to do that is to keep track of the widths, or the number of digits that correspond to each of these, right? So we're going to have some number of whole digits and some number of fractional digits, and those will be represented with W and F. So W plus F gives us the total width of this decimal digit vector, okay? And once we do this, we can represent with a summation, which we'll talk through when we get there, the encoding of, or the translation of this sequence of digits into the actual decimal value that it represents, or the fractional value that it represents. So let's look at a concrete example. And ultimately, we're looking at 10.25, right? So this is the number that we're trying to encode. But we want to think about how would we take just the digits in some order and formally specify the algorithm for calculating the fractional value based on a summation. And so the digits in order are 1, 0, 2, 5. And specifically what we're saying here is W are the whole numbers, right? So this is W and this is the fractional, right? So these are the fractional digits. So there's 2 digits in each of these categories. When we look at the subscription of the digit vector D, we see D sub 1 is 1, D sub 0 is 0, D sub negative 1 is 2, D sub negative 2 is 5, right? So we're saying that this is the 1, 0, negative 1, and negative 2 placeholders, right? Now this is a little bit fancy, right? We're making some assumptions here that will help us out in the actual algorithm that we're going to run, the summation here for computing this. So it just so happens that we're saying that the implicit decimal is between D0 and D negative 1, and we're kind of assigning based on our knowledge of where we expect this decimal place to be. Based on W and F, we're implicitly encoding as part of this subscription notation some information based on where that decimal point is. This is a little bit of a leap, right? But we could further specify this if we needed to indicate how you would compute these subscriptions based on the W and F. But for now, we're just going to trust that we can subscript in this way, and that's going to be important for this summation to work out. Okay, so let's think about the summation. And I'm going to just fill in, I'm going to write over the top of this particular summation. So W is the number of whole digits, and that's 1 and 0 in our case are 2. So W minus 1 is just going to be 1. So we're going to go up to 1 in our summation. And negative F, where F is the number of fractional digits, we have 2 of those, 2, 5, that's going to be negative 2. So I is going to start from negative 2 and go up to 1, okay? And then we're just going to plug in a very similar formula here, and the key thing to recognize is that because we're using 10 raised to the power of our index here, and we have a negative index, that's how we're going to be able to encode these fractional values. So let's just work this out really quickly. We'll start with our first component, which is D of negative 2, and multiply by 10 to the negative 2, plus D negative 1 multiplied by 10 negative 1, and let me make this a little bit bigger, plus or sum D0 multiplied by 10 to the 0, and the last term here of our summation is D subscript 1 multiplied by 10 to the first, or 10. Okay, so then we can plug these values in. So I'm going to substitute D negative 2 is 5, right? D negative 1 is 2, D0 is 0, and D1 is 1, okay? And from here, let's simplify a little bit further. So 10 to the negative 2 is going to be 1/100th, right? So 0.01. 10 to the negative 1 is 1/10, so 0.1. And 10 to the 0 multiplied by 0, this is just going to be 0, right? Even though that would have been 10 to the 0 is 1, and this is just going to be 10, right? So we're almost to a point of being able to do this. So we're saying 0.05 plus 0.2 plus 0 plus 1 times 10 is 10, is going to respond, or is going to encode 10.25, right? And if you're thinking this feels like kind of obvious, that's great. That means this makes sense. We've got a system here, and we can apply the same system, the same formalization to binary in order to represent fractional binary values in base 2. Okay, so that's where we're going next. So in base 2, we're going to apply the same logic, but rather than raising 10 to the power of 1, 2, and 3, or after the fractional decimal point, saying 10 to the negative 1, 10 to the negative 2, we're saying 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, and so on. And our only digits that we have available to us are 0 and 1, right? So what this corresponds to is 1 over 2, 1 over 2 to the squared, or 4, 1 over 8, 1 over 16, and so on, right? And we can think about this as we're increasing the denominator by powers of 2 each time we move further away from our decimal point to the right. Okay, and similarly, like we looked at with integer representations, we think of left of the decimal point as increasing by powers of 2 for each of those positions. Okay, so just to give a quick example here, if we had a 1 in the ones position, a 1 in the 1/2 position, and say a 1 in the 1/4 position, what would we do? Well, we would multiply 1 times 1, and that would be 1, plus 1 times 1/2, 1/2, plus, and hopefully you get you've picked up on this pattern, which was true in integer representations with binary values, which is if there's a 1 in the field, you just take that value and you use that value. The multiplication by 1 really is not important. It's the identity, right? So here we're adding a 1/4 to a 1/2, and this would represent the digit 1 point. So we make this conversion. This is going to be 2 over 4. So 1 point. So let's just do fractions first. 3 over 4, and then 1.75. Right? Is the number that the decimal base 10 representation. I should write a 10 beneath here. 10, and this would be base 10 as well, is the base 10 representation of this fractional binary value. So 1.11 in binary corresponds to 1.75 in base 10. And that translation feels a little bit less natural than thinking in terms of just positive integer values for binary encodings. But what I want to say is if it's the same idea, right? So once you got comfortable with the idea that, okay, we're going to apply that same system of just ones and zeros to the 1s, 2s, 4s, 8s, 16s positions, same idea, but we apply them to the 1/2, 1/4, 1/8, 1/16, 1/32, and so on positions in the decimal points. But otherwise, it works out exactly the same. So one of the things I would like you to try doing is to convince yourself that this is readily possible, and to get some practice thinking in terms of a fractional binary encoding. I want you to try seeing if you can convert this number in binary 1010 dot. So that's where our binary decimal point is, 1010. So that's a base 2 number, to a rational representation in base 10 and a positional representation or a decimal representation in base 10 as well. So I'd encourage you to pause the video here and work through this, and then we'll continue on from this point. All right, great work. So if you take only the numbers where there's a 1 in that position, so the 8ths position, the 2's position, the 1/2's position, and 1/8's position, and we sum those numbers together. So this would be 10 points, and then we sum, and let me just write the fractional value of this first. So 1/2 would be 4/8, right? And this would be 10 and 5/8. Or we could compute that out to the decimal representation as well, which would be 0.125, so 0.5 plus 0.1125, which is 0.625, or 10.625 is what this would have been in a decimal positional representation in base 10. All right, so how do we go from a ratio that's expressed in base 2 to a decimal encoded in base 2 in this representation? Well, long division, right? Now, long division is kind of strange when we're thinking about borrowing and subtracting and carrying out binary operations over even integers in binary. So that's a little bit uncomfortable. So one of the things we can do is we can sort of go back and forth between our understanding of this number in binary and base 2 versus in base 10. And let's try that here. So this first number is 1 base 2 over 100 base 2. So that's not 100 base 2, right? I just made a mistake that is common. When you see 100, you want to think in your head 100, but no, we're talking about base 2. So be careful of this, right? And remember that this is nowhere near 100, right? This is 4, right? So this is the 1's position, the 2's position, this 4's position. So this is 4 in base 2, but when we encode it with our digits, that's 100. So if we think about this in base 10, right, this is equivalent to 1 in base 10 over 4 in base 10, right? And so 1/4 is what we're representing here. And that seems way less frightening than 100 base 2 as the denominator and 1 base 2 as the numerator. But the same rules and the same algorithm effectively applies when we're thinking about long division in base 2. And so let's work through this. So how many times does 4 divide into 1? And the answer is 0, right? So just like we did before, we would say 0. And we've run out of our whole digits here, so I'm going to put in a decimal point, and I'm going to borrow a number here. 0. And so now, and that's effectively borrowing a factor of 2, right? Rather than a factor of 10, we've borrowed a factor of 2. So now the question is, how many times does 4 divide evenly into 2, right? Because this is 2. Well, 0. Again, 4 doesn't divide evenly into 2. So 0 times. So we borrow one more 0 here. And now we're looking at how many times does 4 divide evenly into 4? Well, 1 time, right? And so we enter in our 1 and we make that multiplication, which in the long division of binary is simple because you're only ever multiplying by 1. And so we have 4 here. And we subtract these two numbers and we get 0, right? And so this algorithm is completed. We've effectively worked through the long division of 1 divided by 4 in base 2. And we can check our work and ask ourselves, does this make sense? Because we can go from 0.01 in binary, and I might just add in a little base 2 to be clear that that's what we're talking about here. In a decimal representation of binary, and where our binary decimal point is, or our binary point is what it's often called, because the decimal is associated with decimal number system, our binary point is 0.01. And so we can think about, okay, this is the 2 to the 0 position, this is the 2 to the -1 position, and this is the 2 to the -2 position, right? In other words, this is 1 over 2 position, and this is the 1 over 4 position. And that adds up, right? The only one we had in this number that we produced was in the quarter place value of our encoding. And so we have just a quarter, or this decimal binary representation, or I should say this fractional binary representation, tells us we've got 1/4. Like that's what this binary number represents with the binary point where it is. So we can do the same thing with this second example. But before you do, it's worth thinking about, well, what are the numbers we're actually translating here? So again, in base 2, we've got 1 base 2 over 3 base 2, right? So 3 base 2 is 1, 1. The 1's position, the 2's position, 1 plus 2 is 3. So this is the same as 1 in base 10 over 3 in base 10. And what you know about 1 over 3 in base 10 is that you get a repeating, non-terminating decimal point, 0.333333, and so on. And what you're going to see is in base 2, you also get a repeating value here. Without giving away exactly how the repeating decimal works here, or the repeating binary point works here, I want you to try and work through this on your own and submit that in the response on Gradescope. All right, so you should have a repeating pattern of binary digits. And it'll look a little different than 0.3333 because you only have zeros and ones available. So it's a little surprising how this looks, but hopefully you found the repeating pattern. So this is a brief introduction to fractional values in both base 10 and in base 2. And what we'll be looking at in the next video is, based on this knowledge, how do we actually convert or represent floating point numbers or numbers with fractional values in them in a fixed number of bits. And so this winds up being the really interesting challenge of floating point numbers that I think would actually be fascinating for you to start thinking about before you watch the next video. If you only have a fixed number of bits available, where do you put the decimal point? Or do you even hard code where the decimal point is at all? Or do you use some of your bits to say where the decimal point might be? And when I say decimal point, of course, that's when we're thinking in terms of base 10, but we're going to be thinking when we actually go to encode these numbers in binary, we're going to be thinking about our binary point, which is where the point between the 2 to the 0 and 2 to the -1 positions are in our digit representation. Great work on thinking about fractional numbers, and I'll see you in the next video on floating point encodings in binary.